a sample of galaxies that are redshift 0.1, which are very closely matched in properties to basically redshift 1, redshift 2 main sequence galaxies. So at high redshift, at the sort of peak of star formation in the universe, we know very well by now, this is very popular galaxies, very clumpy. They are kinematic surveys return that they're probably not mergers, at least many of them are rotating systems that are turbulent. And you see these massive clumps of star formation. And so basically we have this very exciting result of this sort of new mode of star formation. And it's very important because it happens at the peak of star formation when most stars in galaxies form. But of course this gives us a problem because resolving the individual star forming regions, the clumps themselves, is very difficult at this distance. And so we need to kind of come up with ways to get around this effort. And that's what Dynamo is. Like I said, it's a sample of galaxies that are closely matched in properties. We originally selected it from Sloan Digital Sky Survey. We just selected the brightest H-alpha emitting galaxies that were not AGNs. And then from those galaxies, we narrowed it down to a sample of about 100 and did a followed-up IFU survey with WISE and Spiral, two Australian telescopes. And then from that sample, we sub-selected sort of the more interesting ones for this particular project for studying the turbulent disk galaxies. And so I'll take you through. We've had sort of targeted follow-ups with things like Keck, OSIRIS, HST, and Gemini, and PDBI. So we feel pretty strongly that these galaxies look a lot like turbulent disks. What I'm showing you here is results from just a few of our galaxies from our Keck program. These are AO-enabled observations with OSIRIS. Over here we have both velocity dispersion maps, velocity rotation, and then stellar surface brightness profiles, which mainly come from R-band continuum with HST. The stellar surface photometry shows these galaxies are a lot like exponential disks, and the rotation agrees with that. They have classic signs of rotation. We can fit kinematic models to these, and we get, that they're always very good with rotation. You can see that in your eye. But then when we look at the velocity dispersion map, we see this mid-tone orange in this map is about 50 kilometers per second, which is much higher, of course, than what you see in normal redshift 0 spiral galaxies, much more like the high redshift turbulent galaxies. And I want to reiterate that the resolution here is about 100 to 200 parsecs in these maps. And so artifacts like beam smearing and things are just not affecting our data significantly, and so we're really seeing high velocity dispersions. We also now have measured gas fractions in a sample of about 20 galaxies in Dynamo. That's what the gray shaded region's in. So this is 3 different distributions that are representative. We have local galaxies in the bottom panel, mid redshift in the middle, and then higher redshift in the top. And we find in Dynamo gas fractions that are consistent with things that you see in like a VIB survey. Sort of 20 to 60% is a typical gas fraction of a Dynamo galaxy. We've done this with CO 1 to 0 observations, and also we have some that are measured by dusk as well. And also, I think this is always, to me, the very basic result that is very clear. And like, if I'm going to stand in front of you and tell you that Dynamo galaxies are similar to high redshift galaxies, then I feel like they ought to look a lot like them. And so we had an HST survey to map H-alpha emission in 10 of our galaxies. And before I show you the full resolution Dynamo maps, what I've done is I've blurred them out to match the resolution at redshift 2. We have over here on your left, we have Dynamo galaxies, and then on the right are some high redshift maps of H-alpha from the literature. And you see very similar properties in both types of galaxies. In Dynamo galaxies, we have these rings of clumps that are popular at high redshift. We have chains of clumps that are popular at high redshift. And so you can also pass these maps, these blurred maps, through any of the sort of quantified definitions of what a clumpy galaxy is. And Dynamo galaxies pass all those correlations quite well. So I think we are building up, basically in every way we look. Dynamo galaxies really do seem a lot like your typical main sequence galaxy that you observe at high redshift. And so we can sort of start looking at them and learning a bit more about them. And obviously, the first thing to look at is effects of resolution and studying the size of the individual clumps. So these are the full resolution H-alpha maps from Dynamo. I always think they're quite beautiful. You see immediately that a lot of information is
gets lost when you go to high redshift, which is in no way surprising. Dynamo clumps, they take on a lot of shape. They are not necessarily circular. They're sort of clustered together. They're obviously smaller when you go to higher resolution. This is, I think, not unexpected. And we can measure the sizes and luminosities of individual clumps, and that's what I'm showing you here. We have H alpha luminosity versus core diameter. Dynamo galaxies are the red points, and then gray would be sort of nearby galaxy, just kind of H2 regions, and they're like sort of a couple orders of magnitude brighter and larger than a typical H2 region. Our sizes of dynamo clumps are pretty consistent with what you get in LINS galaxy surveys, and those are the blue points for the LINS galaxies. So the kind of takeaway from this figure, I guess, would be that the characteristic size of clumps from multiple different groups all seems to be ranging around 100 to maybe half a kiloparsec in size, 100 parsecs, sorry, to half a kiloparsec. What we can do with dynamo that's harder to do with lenses is because we are not dealing with sort of complexities of lens maps, is we can just take those maps I showed you before, the blurred out maps, and remeasure the sizes and luminosities and directly compare that to high redshift galaxies. And we found that if the beam size is basically the same, we recover the same luminosity and same distribution of luminosities and sizes of the high redshift clumps. So I think this is all consistent with, again, this picture, that these are basically the same sort of systems that we're looking at. And we can study systematics of the of individual clumps and how the resolution is affecting things. And so what you see here on the left is a map of a dynamo galaxy at full resolution. And if you concentrate down here, there's this sort of large region where there's a few different clumps. I don't think maybe you can see those arrows out there pointing to them. There's sort of 3 clumps that are close together. And then I would take that map and simulate it as if it were observed in something like the SEN survey, basically an AO observation at redshift 2. You see that that group of clumps gets clustered together and becomes one giant clump. And we find that this is a systematic trend in our data when we run this little experiment. And that's what I'm showing you over there is basically size of the blurred clump on the y-axis plotted against the number of the clumps it's associated with. And we find that the really, really large clumps in the blurry maps are basically always just a function of the geometry of the subclumps. It doesn't appear to be sort of anything physically related to the clumps, and we're looking into that. I think this is not surprising, but I think it's nice to see and to show. We can do, I think, more interesting things by looking in now to the physics of what's going on in these clumps by measuring scaling relations that are basically only possible because we have better data. We have higher resolution data with high signal to noise. And what I'm showing you here is a correlation, a couple correlations between the clump size, average for each galaxy. So every point represents a galaxy and it represents the average clump in that galaxy. So it's about 10-ish clumps per galaxy. The red points are the dynamo disks, and the 2 galaxies are one we sort of independently identify that we think are more consistent with being mergers. And I'm plotting against sigma on these, so velocity dispersion divided by rotation speed of the gas, that's measured with Gemini GMOS data. And then gas fractions measured with Cloud data. And we find, surprisingly, very tight linear correlations between these properties. These clump sizes, just to be clear, are normalized for the size of the disk. And I was really surprised by this. I mean, I was never expecting to see a linear correlation between any galaxy properties. And it looks really good and really tight. And it gets even better because we can come up with an extremely simple physical argument to explain that, and that's what this gray shaded region represents. So there is this, obviously the sort of very popular explanation to explain clumps in high redshift disk galaxies is that you kind of pump up the Jeans link because the gas is very turbulent, and then that gas will, and then the disk is marginally unstable, and the clumps are just a response to that instability. And that picture is nice, but it's mostly supported by kind of coincidental evidence. But here we have a direct prediction from that model. If you make that assumption that clumps are the response simple arithmetic that you can do on a sheet of paper and come up with this correlation over here on the right side where you correlate clump size with sigma on V, and you can then get a sort of secondary correlation by correlating it with gas fraction. You can do this correlation, you know, it's kind of directly falls out of the, what do you call it, the dispersion relation for this. And that's what these gradated regions are. So we have basically exact agreement with this region. The reason it's a shaded region as opposed to a correlation is you can sort of make different assumptions for substitute for the epicyclic frequency and things like that. But nonetheless, very good consistency. And also, I think it's interesting to point out that the two galaxies that are mergers do not agree with us. So when we independently identify something as not being a disk, it doesn't agree with this correlation. So I thought that was pretty interesting and a little surprising. We also are just beginning to look into results on angular momentum in these galaxies. And our results here are really more like suggestive than they are conclusive. So Luca gave a really good introduction to this diagram, to the angular momentum, little j, mass-specific angular momentum plotted against stellar mass in galaxies. And you get a positive correlation if at the same Volz-to-total ratio in this sort of parameter space. Dynamo galaxies, however, are a factor of 4 to 5 low in angular momentum. We think this is maybe, you can make some arguments about why this is an important thing to study. Obviously, if you hold everything constant within a galaxy and then lower the angular momentum, that's going to change things. Maybe make you a little more susceptible to things like conformation. But that's all sort of taking these statements like that with a grain of salt. Nonetheless, I think this is an interesting result and something we're looking to sort of learn more about in dynamo galaxies in the future. So that's about it. I mean, I hope, in summary, I hope I convinced you dynamo galaxies are a lot like high redshift turbulent disks, and that we're finding really interesting things that I think are really complementary to what's being done at high redshift, just due to our better data.
Questions?
Hi, David. I'm Kevin Mundy.
Yep.
I think I know you. So I'm curious about this the suggestion that the high redshift clumps are larger because of beam theory, basically. But then, if you were to use the tomb ray analysis applied to higher redshift, would you get smaller clumps that is actually observed, consistent with the beam moving together?
Right, yeah, so tomb ray analysis, this basically correlation, if you apply the same correlation and input something for redshift 1, redshift 1.5 disk galaxy, you get clumps that are closer to this. You get the preferential clump size should be closer to sort of the dynamo and lens galaxies. I guess if you go to the really gas-rich systems, sort of like 80% gas fraction, then it starts to be, the sizes maybe start to be a little more consistent. But yeah, sort of the intermediate redshift interval, basically they're unresolved by sort of an AO observation.
Well, look, Nazim, other examples of even much more nearby galaxies with turbulent disks, with say 10 times better spatial resolution that you have in Dynamo, to check if your clumps are also going to fragment into smaller and smaller pieces.
Yeah, they're hard to find. Our galaxies are extremely rare. We're dealing with sort of 0.1, 0.01% of the galaxy population. So as you get closer in redshift distance, they basically just become exceedingly difficult to observe, which is why we chose our redshift bands of around 0.1. I think I found one, but it's too far north for me to get interesting data on, so that's difficult.
If there is a
Hello, Casiana. Could you tell us what is your idea of the reason for this violent, these instabilities? What do you think is causing that?
That's actually kind of a good point, just to point out that we have no right to expect it for the violent disk instability model to work so well. It was a model that was designed to represent galaxies with rings by Toomray in the 60s, but it seems to be maybe just a very natural phenomenon. We measure Q in 7 different ways for our galaxies in our sample, and it always averages around 1. And correlations like this seem to work out, so it seems to just be possibly just a sort of self-regulating thing about galaxies. I don't know. I think that's an open question. Plenty of theorists will have answers, but I'm not sure that any of them are right.
Okay, let's thank our speaker again.